I'm Opal Wright. As introduced, I'm a cryptography analyst at Trail of Bits. This is based on the paper that we recently had published. It was presented at the IEEE Security and Privacy Symposium. It won a Distinguished Paper Award, which was pretty nice. This was a joint work with Quang Dao, with Paul Grubbs from the University of Michigan, with Jim Miller, who is my boss at Trail of Bits. And so we'll just dive right into it. Where do Fiat-Shamir attacks show up? Obviously in zero-knowledge proofs. Where do zero-knowledge proofs show up in multi-party computation? Well, there's actually going to be a great talk on this later today that's going to be a lot more detailed than anything I can give. But just for a quick list of things that we see at Trail of Bits pretty regularly, we see a lot of threshold signature systems coming through our pipeline. A lot of clients are implementing them. And we're also seeing a few voting systems, which we start to see a lot of zero-knowledge proofs show up in that context. So rather than diving into specifically the details of what the Fiat-Shamir transform is, how it works, the random oracle model, all those good things, I think we're just going to kind of give an example, and we're going to use sort of the standard Schnorr proof, which you can look at as sort of a, sorry?
Show of hands, how many of you can hear her? This seems very important. Okay, how many of you cannot hear her? Okay, a few of you. Would you mind speaking into
Sure.
this? Thank you so much.
No problem. Thank you. No. All right, any better? Okay, oh good, okay. Sorry about that. So this is a basic Schnorr proof, which you can look at as sort of being a proof for a Peterson commitment without a blinding value. And we're just going to look at the interactive version of the proof. Peggy's going to pick a random value r, compute u is equal to g to the r mod p. She's going to send all of these values to Victor. Victor is going to pick a challenge value and send that back to Peggy. Peggy will then compute z, send that back to Victor. Victor can then perform the verification calculation, and if it passes, then the proof is valid. If the equality doesn't hold, then the proof is not valid and he can reject it. And the Fiat-Shamir transform will basically turn this into a non-interactive proof. So now Peggy still picks R. She still computes U the same way that she did before. But now instead of having Victor send her a challenge value, she's going to compute the challenge value herself using a hash algorithm. And then she's going to compute Z the same way she did before based on that generated hash, generated challenge. And she's going to send it to Victor. Victor can then compute the hash himself, validate the same equation, and if it holds, life is good, accept it. If not, reject it. And what's nice about the Fiat-Shamir transform here is that you've basically taken what was an interactive handshake type protocol and you've turned it into something that looks a lot more like a digital signature. You've turned basically a protocol into a document, which is a really, really nice feature to have. But you can screw this up. In this case, what we're going to do is we're going to do a weak Fiat-Shamir transform. And Peggy's going to pick R just like before. She's going to compute U just the same way. But in this case, when she computes a hash, she's going to leave out H. She's going to leave out this target value. She sends that to Victor. Victor does the calculations. Everything passes. Everything seems good. So what exactly is wrong here? What's broken? And what's broken is that this allows Peggy to forge proofs. She doesn't get to pick the H value, but she can find an H value. And the way she's going to do this, she's just going to generate a couple of random values, U and Z. She's going to compute the hash based off of the values, and then she's going to compute the target value, H, according to this formula here. She sends it to Victor. Victor computes the hash, and you'll notice that taking H to the C gives you U inverse G to the Z. So G to the Z is equal to U inverse G to the Z. It actually checks out. Peggy can't pick what the H is, but she can find a proof that she doesn't actually, she can prove that she knows something that she doesn't actually know. And this is given a lot of times as sort of the quintessential example of a weak Fiat-Shamir attack. And it's been found, it was found in a voting system a few years back. That was the basis of a couple of talks. And actually at trail of bits, we wound up finding this in a production privacy coin, and so we had to work with the customer to get that sorted out. There are a couple of different ways that things fail with the Fiat-Shamir transform. Things get left out. That's been, for the paper that we had published, that was sort of the major thing that we were looking at was things that were left out. Three things that we saw left out quite often: proof statements, target values, like in the last case when H was left out. Domain parameters, so if somebody can go in and change the curve that you're working on or the modules that you're working with. And sometimes generated challenges. So if you have multiple steps to a protocol, you invoke the Fiat-Shamir transform multiple times, you have to take those generated challenge values and incorporate them into later challenges. So that's what we tend to see, and the example that we're going to give for a modern Fiat-Shamir, or a modern zkp system Fiat-Shamir transform is bulletproofs, which is a fairly nice generalization of the Schnorr proof that we were just discussing. These are basically used mainly for range proofs. They're a lot more flexible than that, but they have a lot of very useful features, and they operate on what are called vector Peterson commitments, which are a generalization of Peterson commitments, which is sort of how we were kind of discussing the Schnorr proof there a moment ago. The proofs are based on what's called an inner product argument, and they're useful in the fact that they're small. The range proofs are useful for multi-party signatures. The multiply to add portion of a lot of proofs, or a lot of these systems require range proofs, so they're very useful there if you're not using other techniques. And they also show up in voting systems occasionally where you're trying to show that the number of votes is less than the total number of voters, things like that. And so getting into what a vector Peterson commitment is, you're basically given a group, usually it's an elliptic curve group. You have a list of generators that are unrelated in the sense that the discrete logs of any one with respect to the others is not known, and a hiding factor. And your commitment is basically just the product of each generator to the power of the committed value from the vector V. And then you have your hiding value H at the front with a randomized gamma value to act as hiding. But if you got rid of the H and the gamma, the hiding goes away and it just becomes binding. The inner product argument, which is the basis for the bulletproofs, basically it allows Peggy to commit to two vectors, and she can basically show that she knows, after publishing a couple of values, she can show that one, she knows what the she knows what the secret vectors A and B are. She can show that she knows what R is, what the inner product R is, and she can show that the vectors she committed to correspond to this published value. And these are interactive proofs, which is where the Fiat-Shamir transform is going to show up a little bit later when you try and make it non-interactive. But it's this ability to show that you know the inner product of the two vectors that really winds up being useful. And that gets turned into this range proof fairly quickly. So Peggy has a secret V, and it has an associated binary vector A sub L, and she has a secret value gamma. She's going to publish what's essentially just a standard Peterson commitment, a hiding Peterson commitment V to her secret value. And she wants to prove the following three things. First of all, she wants to show that the commitment V corresponds to her secret V. She wants to show that the binary vector for V, this A sub L, the inner product of that with a vector of powers of 2 comes out to equal her secret value, which is basically to say that A sub L is the binary representation of V. And then she wants to prove that A sub L actually is binary. So she needs to show that A sub L is not only is it a representation of V, but it's a binary representation of V. And those are the three things. And if you can prove those three things, you've essentially proven that the value that Peggy committed to has at most n bits. So yeah. In terms of how it actually works and all of the details, there's this wonderful diagram, And no, we're not going to get into all of the details here because this is a 15-minute talk, and I know we're already over time. So we're not going to get into it because we don't really have to get into a lot of the details here. We can actually just look at one little thing here. You'll notice the highlighted section, it says y is equal to the hash of a comma s. And y is one of the challenge values that's generated. And if you look into the paper, a and s are basically commitments to the binary vector and to a blinding vector. What you'll notice is not included in there, there's no commitment to the actual value v, and there's no commitment to n. So that's what was in the original paper. There's since been a CVE filed against the original bulletproofs paper, and they have updated it to include y is equal to the hashment of st, the statement, and in this case, st is the commitment v and the bit length n. And it turns out, we had talked about the Schnorr proof, how you go about doing that. This is actually very similar. The structure is pretty much the same. You're going to reverse engineer a target. So we're going to generate a proof with a bunch of randomized values. We're going to pick randomly selected a sub l, s sub l, s sub r, t1, t2, tau 1, tau 2, tau x, and we're going to compute a whole bunch of values according to the actual proper protocol, the actual proof system. And that's going to generate 3 challenges, x, y, and z. And in the end, we wind up getting 2 simple equations, and we solve those to find our v and gamma values. And then we can set v equal to that, and we have a proof that will validate despite the fact that we don't know the actual, we haven't actually committed to a value and shown that it's within the range. And this is something that we actually did find in the wild causing a problem. It was on the Incognito chain. It allowed for a minting attack. So people could generate money on the chain, which is, I don't know, kind of bad. So yeah, in terms of where to go with this in the future, and I'm sorry I'm skipping over a lot of details, but we've kind of done, during the research product, during the research process, we discussed a lot of different things about how can we actually help prevent these sort of issues in the future. There were a lot of different causes and a lot of different issues associated with why these problems came up. This was not the only system we found problems with. But some of the things that we thought might be useful, transcript specification tools. Sometimes what we saw were people who implemented these programs and they missed branches or things like that, and so a particular value might not get included because it wasn't included in both the if and else branches to be incorporated into the transcript. So something that would allow you to specify the transcript and make sure that everything gets included. Context-inclusive serialization libraries, so if you're using a specific elliptic curve, maybe the elliptic curve parameters get included every time you include a point from that elliptic curve. And it would probably be a little bit of a stretch to see someone generate an analysis tool, a static analyzer, that could actually go in and say, okay, you're doing your verification function here. Here are all the things that go into the transcript. Here are all the things that you're using in your final validation checks. Here are the things that aren't used. Are you sure you've included everything? But might be something worth looking into. In terms of the first two, Trail of Bits actually has something possibly in the works on this, so we'll see hopefully in the next few months if something comes out of that. But overall, the main things to realize, Fiat-Shamir is actually a lot more subtle than people give credit for. It's really easy to screw things up, and a tiny mistake can completely obliterate your security. If you want to prevent this from happening to you, there are a couple of things that you need to do. Using good libraries. Merlin's available for Rust and C. Using a good library isn't enough. It won't prevent you from leaving something out, but it can at least make it easier to avoid the sort of things that show up when you try to roll your own transcript solution. Have good code reviews with multiple reviewers. I'm not saying have good code reviews with people like Trail of Bits, although you can. but I don't want to turn this into a marketing opportunity. But just have multiple people on your team who actually know the math, who know the cryptography, looking into this deeply. That's just absolutely critical, and I think it's something a lot of teams kind of overlook. Make sure that you actually write and specify all of your Fiat-Shamir inputs and outputs. Make it something that you can test against to make sure that it's something that you can actually, it's something that's documented and you keep up to date. Also remember, if you can transmit it, you can hash it. If it's something that can be put across the wire, it's something that can be included in the transcript. There's no reason to be stingy about what goes into your Fiat-Shamir transform. Yes, you have to hash a few more values. I have not seen a system where the hash is the bottleneck for a zero-knowledge proof. And finally, don't trust the papers completely. We've had quite a few situations where we found papers that left critical values out of the Fiat-Shamir specification. So don't trust the papers 100%, of course, except ours. So, yeah.
That's great. Thank you so much. I think you'll have to stay with us for a bit for any questions. I see quite a few hands.
Thanks for the talk.
Yeah.
Do you think there's a world where people would write extractors as part of the code, as kind of the testing to see that you can actually, extract the things you want trying to prove proof of knowledge of?
Do people write like the actual extractors?
Yeah, like people as part of, like, let's say, the implementation, as part of the testing, you would actually write like the extractor from the security proof.
I've not seen anybody actually write an actual extractor based on like a security proof, anything like that. I've never seen that come across the door at work. But if somebody wanted to try that, I suppose that'd be great. I think this is one of those things that's a little bit more subtle because a lot of your extractors are based on the idea of everything being done correctly. And this is obviously something where somebody's missing a step along the way. So having a generalized extractor that can understand what's missing and what's not is a little more of a difficult problem. Does that make sense?
But I guess, I mean, like in some senses, if you don't hash in enough stuff, then you won't be able to extract the things you're trying to prove proof of knowledge of, right, in some sense. So kind of if you show that you can extract, then it gives you some confidence.
Okay. Yeah, if you can write an extractor, obviously you've definitely goofed up, yeah.
Because if you don't hash enough stuff, when you program the random oracle, you can write like the code that
I mean, I'm thinking.
programs the random oracle and learns.
The extractor is completely incorrect.
But I mean, you together with the programming of the random oracle.
If y'all can discuss on the mic, it would be great for like a nice recording, like a self-written ChatGPT paper.
Okay.
Yeah. Next question. Yeah.
Thanks. You kind of alluded to that, but should the recommendation be any different than just hashing everything from the very beginning of the transcript between the two parties? Any downside to that except for some performance overhead?
I'm sorry, can you repeat?
Would it make sense to just hash everything from the very beginning of the transcript between the two parties?
Yeah, you usually want to hash everything that's in the transcript. The trick is that a lot of, in some of these cases, there are questions about what actually is part of the transcript. One of the things that we didn't get in here that I actually had an original, or I had in an early version of the slides was the Zalewski verifiable delay function. And that was, we found an attack based on an attack on the verifiable, on the VDF based on a weak Fiat-Shamir issue because in the original paper, it was specified with the time parameter or the difficulty parameter as just being sort of a global fixed value. And as it was being implemented out in the field, that delay parameter was being modified all the time. Each particular puzzle had its own T parameter, and so that wasn't getting included in the hash. So it is part of the transcript in a certain sense, but everybody was treating it as something that was just essentially a global variable, a global domain parameter, and so it didn't occur to anybody to include that. So yeah, absolutely, you should include everything in the transcript. It's just that some folks don't realize what goes in the transcript.
Mm-hmm. Yeah, thank you.
Hello. Do you see something that can be done within the research community to kind of prevent these mistakes that are sometimes, like these are minor details that you might get wrong as a researcher, but they have like critical consequences in practice, and researchers might not always be aware of all of that. So is there something that researchers can do, like write better specifications?
Yeah, I mean, specifications are definitely a part of it. I think there are sort of two approaches you can take to it. One is to be very careful and go in and say, okay, we're going to tell folks that you can use the Fiat-Shamir transform to do this. And so you can do that one of two ways. You can say, and here's exactly how you do it, and make sure you sit down and do the research on top of everything you've already done to come up with this new and novel and interesting system, and make sure that you've nailed down every single parameter, and actually have a specification and really work hard to make sure you get it right. Or the other option is to say, hey, you can use the Fiat-Shamir transform. Please consult a good reference on that. Ideally, it would be the former, but with the latter, at least you're less likely to give people bad information. Don't specify something unless you've done the research to specify it, I guess is what I would say. If you don't want to go through the process of making sure that you have all of the inputs properly listed out, just leave it alone. Say, hey, you can use the Fiat-Shamir transform. Please find a good place to figure out how to do that.
Hi, this is interesting work, and I think it's very important, obviously, for people who are implementing things in practice to be aware of these issues. I was just going to make a comment. It's not really about your talk, but about the researchers and mistakes in papers and whatever. That depending on the context, you don't necessarily need to include everything, and so that, researchers who are writing papers may be aware of that, and maybe they're cutting corners, and maybe it's intended for one application and then used as another. I mean, just as two examples, like you talked about including the prime in the hash, and if the prime is a global parameter that should never be changed, then technically you don't have to. And for signatures, if you're building a signature from a Sigma protocol, if you don't include the statement, then somebody can make up a signature on a random public key, but they won't be able to forge under your public key. So, right. The moral is the same. That in the end, the people implementing have to understand these issues. But,
exactly.
I just wanted to point it out.
Great. Thank you so much. Moving on. Thank you, Opal. Thank you for your time. Thank you.